Hello and welcome to the channel. In this video we'll take a hands-on look at OpenStack, an open source cloud platform used to build and manage private and public clouds. If you understand the core concepts of OpenStack, you'll be well equipped to work with any major cloud provider, whether it's AWS, Google Cloud or Azure. I'll start by diving into a practical demo using DevStack to set up our environment. You'll see how to create projects and users, deploy virtual machines, expose them to the network, configure security groups, assign floating IPs, and even set up a load balancer. The goal is to give you a clear sense of what working in a cloud environment looks like. And to wrap things up, we'll explore some basic automation using Terraform. My name is Filip, thanks for watching and I hope you enjoy the video. There's a lot I'd like to show you, but we'll take it step by step. This video is just the beginning, meant to give you a hands-on feel for how OpenStack works. Think of it as your starting point. In future videos, we'll dive deeper into individual components and features, exploring more advanced topics as we go. So, what exactly is OpenStack? OpenStack is a modular open source cloud platform made up of various components, each responsible for a specific part of the infrastructure. In today's demo, we'll be working with a few of those core services. Horizon, the web-based dashboard. Nova handles compute and VM lifecycle. Neutron takes care of networking. Glance manages images. Cinder provides block storage. These building blocks come together to form a flexible cloud environment, one that we'll be exploring piece by piece, starting right now. Let's log into OpenStack Management Dashboard as an admin user. This web-based GUI is powered by Horizon Service. First, let's create a new project. A project acts like a logical container for organizing resources. Each project has its own VMs, network, storage, quotas, and so on. You can use projects to isolate environments like dev, QA, prod, or isolate applications at an infrastructure level. To set up a new project, I'll go to Identity, Projects, and click Create Project. Let me name it Filip and hit Create. Next, we'll create a user. Users authenticate with OpenStack Cloud and interact with its services primarily through API, CLI, or the Horizon Web Dashboard. I will go to the Users tab, then click Create User. I will call this one Filip, set a password, select our new project as the user primary project. That's where the user will be directed after login. Note, users can have access to multiple projects. Now for roles. Roles define permissions within a project. Here I've selected the admin role, which allows full control over resources. Let's click Create. With a user account in place, we can now move on to creating virtual machines. In the cloud, virtual machines are usually created from images. An image is essentially a pre-configured template that includes an operating system and optionally some pre-installed software. Instead of manually installing the operating system from an ISO file every time, cloud platforms like OpenStack use images to quickly provision new VMs. This not only speeds up deployment but also ensures consistency across instances. To launch a new VM in OpenStack, the first step is to upload a cloud image to Glance service. Glance is OpenStack's image service. It stores and manages VM images so they can be used when launching new instances. I will go to Admin, Compute, Images. I've already downloaded an Ubuntu cloud image. You will find the download link in the description below. Let's load the image. I will click Create Image, name it Ubuntu, select the file. Here I'm choosing QEMU KVM image in a copy on write format. Let's set the minimum disk size to 8 GB since the image requires at least that. I will make it public so other projects can use it. Then let's hit Create. Okay, the image has been loaded into OpenStack image repository. This means that when you launch VMs from a pre-baked image, every instance will be identical, which is great for consistency. But what if you need to customize each instance, like assigning a static IP, adding SSH access, or installing specific software? That's where Cloud Init comes in. Cloud Init is a tool that automatically configures an instance during its first boot using something called a user data script. With this script, you can set the hostname, inject SSH keys, configure networking, create users, install packages, run shell script, and more, completely unattended. It's a powerful way to automate configuration and ensure every instance is provisioned exactly the way you want it right from the start. Now let's log out and log back in as our newly created user. Notice the top right corner. It now shows Philip as the active user, and in the upper left you'll see the current project, Project Philip. At this point we don't have any resources yet. So what's the first step? Networking. Let's head over to network topology. OpenStack networking is managed by a component called Neutron. It handles all virtual networking, including subnets, routers, floating IPs, and security groups. OpenStack networking model closely mirrors how real-world networks work. Here's what we currently have. An external provider network, which connects OpenStack to the outside world, and a shared network accessible across multiple projects, useful when VMs from different projects need to communicate. In OpenStack, a network acts like a virtual layer to switch. Let's create our own private network for this project. I'll go to Networks and click Create Network. Let's name it PhilipNet. Next, we define a subnet, which is a layer 3 construct. It provides the IP address range, gateway, DNS settings, and DHCP configuration. I will name the subnet Philip subnet, set the address range to 10/24, and use the first address in the range as the gateway. Let's leave DHCP enabled so our instances can auto-assign IPs. Once we hit create, the new network will appear. If we return to Network Topology tab, you'll see our newly created private network, isolated from other projects and ready to host our virtual machines. Now let's create two virtual machines using our Ubuntu image. To do that, I will go to Instances, then click Launch Instance. There are a few parameters we need to configure. Instance name and count. I will name the instance VM and set the count to 2. We will create two identical VMs. OpenStack will automatically name them VM1, VM2, and so on. Source. This defines the image used as the base template. I will select the Ubuntu image we uploaded earlier. The disk size will default to the image's minimum requirement. There's also an option to delete the volume when the instance is terminated. This is useful for temporary workloads. If set to no, the volume persists even after the VM is deleted. Flavor. This determines the VM's virtual hardware, CPU, RAM, and disk. We'll choose a flavor with 1 virtual CPU, 1 gig of RAM, and 10 gig of disk, which is enough for this demo. Network. We'll attach the VM to the private network we created earlier. I will skip ports and security groups for now. We'll get back to those later. SSH key. Since Ubuntu Cloud Image use SSH key authentication by default, we need to import an SSH public key. I will click Import Key Pair, name it Philip Key, select SSH as key type, copy the public key from my local machine, and then paste it here. Customization script. This is where Cloud Init comes in. Cloud Init runs this script after the instance boots. It allows you to automatically configure and personalize your VM on first launch. This is how you can update packages, install software, set host names, create users, configure networking, or run any commands you typically execute manually after login. It's a key part of cloud automation and ensures your instances are ready to use immediately after provisioning. I will load a simple script that does two things. Sets a password for the Ubuntu user and allows password authentication. This is useful for this demo, though not recommended in production. It also installs and configures the Caddy web server, which will serve a page displaying the VM's IP address over HTTP. Using a startup script like this is great for automation and lightweight deployment, especially in development environments. However, there are downsides. Your VM has to wait for packages to download and install. If the network is down or the source is unavailable, the setup fails. For production environments, a better approach is to bake your application into a custom image using tools like Packer. This ensures faster boot times and consistency. Your application is pre-installed and ready as soon as the VM starts. Alright, with everything configured, let's click Launch and wait for the instance to be created. Okay, our two instances are ready. Let's go back to network topology. You'll see both VMs attached to our private network. each assigned an IP from the 10/24 subnet. But what if we take a closer look at the diagram? Something is missing. The VMs don't have internet access. Let's confirm that. I will list the instances and then open the console for VM1. Normally, you'd use SSH to connect, but since our private network is isolated, we'll use the console instead. Here's the login prompt. I will log in as the Ubuntu user, and we are in. Let's try picking Google DNS at 8.8.8.8. No response. That's to be expected. Our private network has no route to the outside world. To fix that, we need to create a virtual router to bridge our private network to the public internet. I will go to Routers, click Create Router and name it Router 1. Next, I will connect it to external network. In our case, it's called public and enable source NAT. I will click Create and the router is ready. Back in the network topology, the router now appears with an IP address from the public network, but we are not done yet. Currently, the router isn't connected to our private subnet, so I will open the router's interface tab and add a new interface, linking it to our Philips subnet. Done. Now, in the topology view, the router has two interfaces, one facing the public network and one connected to our private network. Thanks to SNAT, traffic from the private network can now be translated and routed to the internet. Let's test it. Back in the console for VM1, I will try pinging 8.8.8.8 again. And it works! Now any VM in our private network can reach the internet. From the outside world perspective, all outbound traffic appears to come from the router's public IP, in this case 192.168.81.1. Okay, but how do we access an instance from outside OpenStack? For that, we'll use a floating IP. Let me show you how it works. First, I will go to the Floating IPs tab and click Allocate IP to Project. Then I will click Allocate. A new IP address is now assigned from the public subnet. At this point, it's not yet linked to any instance. Next, I'll go to Instances tab, select VM1 and choose Associate Floating IP. I will pick the IP we just allocated and click Associate. Now, if we look at the instance details, we'll see that VM1 has two IP addresses, one from the private network and one floating IP from the external network. So what's happening here? The router is performing one-to-one NAT. It's mapping the floating IP to the VM's internal IP, effectively exposing the VM to the outside world. It's important to understand that the floating IP isn't directly assigned to the VM itself. It's actually linked to the router, which then forwards traffic to the correct instance inside the private network. From now on, this VM is reachable externally using the floating IP. So to summarize, if a VM doesn't have a floating IP, any outbound traffic will be NATed and appear to come from the router's external IP. If, however, a VM has a floating IP, it gets a dedicated external address, making it directly accessible from outside OpenStack. Okay, let me try connecting to the VM from outside OpenStack through the external floating IP. Still no luck. The reason for this is OpenStack's security group, which function like a virtual firewall for your instances. By default, they block all incoming traffic to the VM's network interface. Although the floating IP provides the external address, you'll need to explicitly add rules to the security group to allow specific types of inbound traffic, like SSH or HTTP, to reach the VM. Each instance is assigned one or more security groups. By default, all incoming traffic is blocked and all outgoing traffic is allowed. Mind that return traffic is allowed if the instance initiated the connection. So, if you want to allow external SSH access, you need to explicitly allow inbound TCP traffic on port 22. Let's fix that. I will go to Security Groups and click Create Security Group. I will name it SGSSH. Then I will add a new rule, direction ingress, port TCP 22 for SSH, source, anywhere, that's quad zeros. Then let's click Add. This security group allows all outbound traffic, and for inbound it allows only SSH connections from anywhere. Everything else is blocked. For it to work, let's attach this group to our instance. I'll go to Instances, choose VM1 and click Edit Security Groups. I will remove the default group and add our new SGSSH. I'll do the same for VM2. As you can see, a single security group can be reused across multiple instances. Let's test the connection again. And we are in. SSH works. Next, let's expose the second instance to the outside world. First, I will allocate another floating IP from the external network. Then I will go to VM2, click Associate Floating IP, and select the newly allocated IP. Done. At this point, both VMs have floating IPs and should be reachable from outside OpenStack. Let's try connecting to VM2 via SSH. Success. Now let's test the KDE HTTP server we installed earlier. I will run curl against the external IP of VM1. Doesn't work. That's expected. We've only allowed port 22 for SSH so far. Let's create another security group for HTTP traffic. I will go back to Security Groups, click Create, and name it SGWWW. Then I will add a new rule, direction ingress, port TCP80 for HTTP, source anywhere, and click Add. Now I will attach SGWWW to VM1 again using Edit Security Groups and add it in addition to SGSSH. Remember, instances can have multiple security groups assigned and the rules from all of them are combined. I will repeat the same steps for VM2. Time for the final test. CURL to VM1 works. CURL to VM2 also works. Both VMs are now reachable from outside OpenStack over both SSH and HTTP, thanks to our floating IPs and properly configured security groups. Let's go one step further and set up a load balancer in front of our two VMs. I will navigate to Network, Load Balancers, and click Create Load Balancer. First, we need to specify the subnet where both our VMs and the load balancer will live. That's our private subnet. Then we set up the listener. It's the front-end component that receives incoming traffic. I will set it to listen on HTTP port 80. I will also enable insert X forwarded for. This adds a header to HTTP requests, allowing our backend servers to see the original client IP. Now we create the backend pool. This is where we configure load balancing algorithm. I will choose round robin so traffic is distributed evenly between the VMs. Pool members. I will add both of our VMs, each listening on port 80, which matches what our KDE servers are running. To keep the load balancer aware of VM health, we'll configure a health monitor. I will set the type to HTTP. The balancer will send a simple HTTP GET request and expect a 200 OK response. If a VM doesn't respond or returns an error, it will be marked as unhealthy and removed from the pool temporarily. I will click Create Load Balancer and after a short wait, we'll see the balancer status change to active. At this point, the load balancer is functional, but keep in mind, the virtual IP of the load balancer belongs to the private network, just like the VMs, so it's not yet reachable from outside OpenStack. To expose it publicly, we need to assign a floating IP. I will go to Floating IPs, allocate a new IP from the public pool, and then associate it with the load balancer. Now the load balancer is accessible from outside OpenStack, just like we did earlier with individual VMs. Let's test it. I will use CURL to call the load balancer's external IP. It works. Requests are being balanced across both VMs thanks to our round-robin setup. Now let's simulate a failure. I will shut down VM1. If we check the backend pool status, we'll see that VM1 is marked as error after failing 3 consecutive health checks. However, the application is still up and running because the load balancer automatically redirects all traffic to the healthy instance. This is one of the core benefits of using a load balancer. It not only distributes traffic but also monitors the health of your backend services and helps maintain availability even when one node fails. So far, we've seen how to set up projects, users, images, virtual machines, and networking in OpenStack manually through the Horizon dashboard. But the true power of cloud isn't just in spinning up virtual machines. It's in doing it efficiently, reliably, and repeatedly. And that's where automation comes in. Instead of clicking through a UI every time you need a VM or network, you can describe your infrastructure as code. And for that, we'll use Terraform, a popular open source tool. Terraform lets you define your infrastructure using simple configuration files, making it easy to recreate environments consistently and with minimal effort. Your infrastructure becomes version-controlled, shareable, testable, and reproducible. The beauty of Terraform is that you don't have to tell it how to create each resource. Instead, you declare the desired state. For example, I want 2 VMs, and Terraform figures out the steps to get there. In this demo, we'll use Terraform script to spin up a VM, assign it a floating IP, configure security groups, and run a startup script, all automatically in one go. Let's walk through a simple Terraform configuration file. Keep in mind, this video isn't a full Terraform tutorial. I just want to show you what's possible when you shift from manual cloud management to automation. First, Terraform connects to OpenStack using a provider. We specify our authentication details. Then we fetch information about an image named Ubuntu, a VM flavor called M1 Small, and a network named PhilipNet. Next, we define 2 security groups, one for HTTP, allowing TCP traffic on port 80 from any IP, another one for SSH, allowing TCP traffic on port 22 from any IP. We then define a startup script. This will run automatically when the VM boots. We create a network port on the Philip network and attach both security groups to it. This port will be then connected to the VM. Now we define our VM. We name it Ubuntu KDE, set the image flavor and SSH key, attach the network port, and inject the startup script as user data. Finally, we allocate a floating IP and associate it with the VM so it's accessible from outside OpenStack. Now let's run our automation. First, we run Terraform init. This is a one-time step that prepares the project, downloads the required provider plugins, and sets up the backend to store Terraform state. Then we run Terraform apply. This compares the desired state from our configuration file with the current infrastructure. It shows a plan. In this case, Terraform will create 8 new resources. Let's confirm. Terraform is now applying the plan. Done. Here's the external IP of our newly created VM. Let's try to SSH into it. Works perfectly. If we check the Horizon dashboard, we'll see our instance under Compute Instances. It's using the image, flavor, and SSH key we specified. Both of our security groups are attached. Under Floating IPs, a new IP has been allocated and assigned to our VM. The startup script also ran successfully. To verify, I'll open the instance console and log in using the credentials from the script. There it is. And that's the magic of cloud automation. The best part about using tools like Terraform is that they bring efficiency, repeatability, and reliability to your infrastructure. Whether you are deploying a single VM or a complex application stack, you can automate the entire process with confidence. Cloud infrastructure is no longer just about provisioning. It's about managing it as a code. And that's what makes modern cloud systems so powerful. There are several ways to install OpenStack, but today I'm going to show you how to set it up using DevStack. DevStack is a collection of scripts and tools designed to help you quickly install and run OpenStack in a development or testing environment. It's a great choice for learning because it allows you to spin up a full OpenStack cloud on just a single machine. Before we start, there are a few things to consider. In real production environments, OpenStack is typically installed directly on bare metal servers. However, for this demonstration, I'll be running OpenStack inside a Hyper-V virtual machine. I've allocated 16 GB of memory and 12 virtual CPUs to the VM. If you are running OpenStack in a VM, it's important to enable MAC address spoofing. This allows the VM to change the source MAC address for outgoing packets, which is necessary for allocating floating IPs. Without MAC spoofing enabled, floating IPs simply won't work. You should also enable nested virtualization, assuming your CPU supports it. Nested virtualization allows you to run virtual machines inside other virtual machines. Without it, OpenStack can only run using software emulation via QEMU, which is extremely slow because it lacks hardware acceleration. With nested virtualization, OpenStack can act more like a true hypervisor, giving you near-native performance for nested VMs. Alright, let's start up the VM. I'm running Ubuntu 2204 LTS here. Let's make sure nested virtualization is enabled for the VM. On my system, I did this by loading the KVM AMD module. You can verify that it's enabled by checking the relevant KVM parameter. It should return a value of 1. Now let's proceed with the installation. First, I'll create the stack user, then update permissions of the OpenStack folder. Next, grant passwordless sudo access to the stack user. Finally, I will switch to the stack user account. Next, we'll clone the DevStack repository. After that, I will go to the DevStack folder and create a local configuration file where we'll set up our OpenStack components. I already have one prepared. In this configuration file, I define the IP address and set passwords for the various OpenStack services. For this demo, everything is running on a single server, but in a production setup, you typically have separate servers handling different roles. Here's what else we configured. We set up OpenStack to use IPv4 only. Here we enable support for security groups in Neutron. Then we specify the CIDR block used for floating IP addresses. Here we restrict the allocation pool so that only 29 IPs from that available range can be used, rather than entire /23 subnet. Then we define the physical network interface that connects to the external network. In this setup, we only have one interface. But in production, you usually have multiple. Since we already have a network gateway, I will disable OpenStack's gateway creation in the config. Here we set up a bridge connected to the provider network and map it to the public network in Neutron. Here we enable additional components like Octavia load balancer. With everything set, let's run the stack.sh script to install OpenStack using our prepared configuration. Depending on your hardware, this can take up 10 to 15 minutes. I will speed up the video. And we are done. The installation is complete. Let's log into the OpenStack dashboard, and we are in. Keep in mind that DevStack is designed as a developer tool, not for production deployments. The setup is not persistent and typically won't survive a VM reboot. In future videos, I'll guide you through creating a more robust production-styled OpenStack environments. And that's it for today's hands-on introduction to OpenStack. I hope this walkthrough has helped demystify how private clouds work, from setting up projects and networks through deploying VMs, securing your environment, exposing services, to automating it all with Terraform. Remember, everything we covered here just scratches the surface. OpenStack is a huge ecosystem with a lot of possibilities, and in future videos I'd like to dig deeper into topics like multi-node setup, storage options, advanced automation, and real-world deployment guides. If you found this video helpful, please give it a thumbs up. It really helps the channel grow. Got questions or want to see specific OpenStack feature in action? Drop a comment below and I'll do my best to cover it in upcoming episode. Don't forget to subscribe and turn on the notifications so you don't miss the next deep dive or tutorial. Thanks so much for watching. I'm Filip and I'll see you in the next video.